Hello algebra students, this is your flipped video lesson on solving systems of equations by substitution. If you'd like to take a look at the criteria for success and what we'll be learning, you can pause the video here and review this list. Okay, so before we get into a system proper, let's just talk about the fact that substitution is an algebraic method for solving systems, and let's look at why it works. So let's start with not a system, but just one equation. And I'll ask you, how many variables do you see in this equation? Well, we've got an x, we have an x and we have a y. So we have two variables. Can we solve an equation that has two unknown variables? No, we can't, not unless we have some more information. So what if I told you that y is equal to -1? Could you then solve this equation for the value of x? Of course you could. So you would simply take y equals -1 and you would substitute it into the equation wherever you see y. So here's a -1 where y was. And now we have how many variables in this equation? Just one variable. If we have just one variable, we can solve for it. So at this point, we've got 3x minus 1 equals 11. We would add 1 to both sides to get 3x equals 12, divide both sides by 3, and we have x equals 4. So if we can eliminate one of the variables, then we can solve for the other variable. What if we weren't given y equals 1, but we were given y equals x minus 1? Could you find the value of x? Well, let's try. We have a definition for y. Y is equal to x minus 1. So everywhere we see y in this equation, let's substitute in x minus 1. So we have 3x plus y is equal to x minus 1 equals 11. Now take a look at this equation. How many variables do we have? We have an x, we have another x. The y's have been eliminated. So we have only one variable. If we have only one variable, can we solve for that variable? Absolutely. So let's go ahead and do that. We have 3x and 1x. That's 4 x's. Minus 1 equals 11. If I add 1 to both sides, I'll have 4x equals 12. And divide both sides by 4, and I have x equals 3. So in the same way that we can substitute a value in for a variable, we can also substitute in an entire expression for a variable in order to eliminate that variable so that we can solve for the other variable. How does that help us in a system of equations? Let's take a look. These are the exact same two equations that we were just looking at. We could graph this system and come up with two lines, find their point of intersection or the point that they both share, the point on both lines, and come up with a nice solution with an x and a y value. But what if we don't want to graph it? What if we don't like graphing? Or what if graphing in this particular case is not particularly convenient? Then we can use the algebraic method of substitution to solve this equation, this system of equations. And we do that by solving first for one of the variables. In this case, one of our equations is already solved for y. Y is equal to x minus 1. So just like we did before, we'll substitute in x minus 1 wherever we see y. And we'll solve for x. So again, we already did this. So we have 4x equals 12 and x equals 3. So what does that do for us? Now that we have x equals 3, we know where these two lines intersect, or the point that these two lines share has an x value of 3. So now I can choose either of these original equations and substitute my 3 back in and find out what is the y value at that shared point where x equals 3. So you can choose either one. It's completely your choice. I'm going to choose the one that would be a little bit easier, this one right here, because there are no coefficients for my variables. So y is equal to x is 3 minus 1. So y is equal to 3 minus 1 is 2. At the point where these two lines intersect, the point that these two lines share, my x value is 3 and my y value is 2. The great thing about systems of equations is there's always a way to double check your work. And I definitely want to double check. So I substituted in my x equals 3 value into this equation here and found out that y is equal to 2. So now I want to substitute my solution point into this first equation and make sure that this solution is also a solution to my first equation. Because remember, in a system of equations, the solution is the point that solves both of the equations. So let's do that. Wherever I see x, I'm going to enter 3. I'm going to substitute in a 3. And wherever I see y, I'm going to substitute in that 2. And let's see if I get a true statement. Let's see if 3, 2 is a solution to this first equation. That gives me 9 plus 2 equals 11. And we can see quickly that that, in fact, is a true statement. So 3, 2 not only solves the first equation, but it also solves the second equation. And it is therefore our solution to our system of equations. Okay, so let's summarize what we just did here. The first thing we did was we took the expression x minus 1, which was equal to y, and we substituted that expression into the other equation and solved for y. So we substituted and solved. Then we had a value for x. We substituted that value for x into the other equation, and we solved for the other variable, for y. So that gave us an xy solution point, which we then substituted back in to the first equation just to double check that it was also a solution to that first equation. So those are the steps for the algebraic method of solving a system by substitution. Let's look a little bit more closely at this first step, because in this first step, substitute and solve, we have some decisions to make. Okay, I have 3 systems of equations here. I'm actually just going to talk about this one for right now. So in this system of equations, our decision about which expression to substitute in for which variable is made very easy for us because x has already been solved. So that makes our work so much easier. If x has already been solved for y minus 3, then wherever I see x in that first equation, I can just substitute y minus 3. Then I will have an equation with only one variable, and I can solve for that variable and then continue through my substitution process. So let's skip ahead here. I want to look at some other examples. In this system of equations, no variable has been clearly isolated, so I'm going to have to do that work myself. But I'm going to choose wisely. It looks like y has no coefficient, so if I were to solve for y, it would make my job a little bit easier because I'd only need to take one step. If I subtracted 3x from both sides of that equation, I would have y equals negative 3x plus 3. And I just solved for y. I now have an expression that I could plug in to that second equation wherever I see y. Okay, same thing in this system of equations. There's one that makes a little bit more sense. I would choose this equation right here, and I could solve for x or y, but I'm going to solve for x because it's just a little bit easier. It makes my job a little easier because I can add y to both sides of the equation. That would give me x equals y minus 1. Now I can take y minus 1 and substitute it into the second equation wherever I see x. I want to emphasize here that you don't have to make these choices that I'm making. You can choose either equation and solve for either variable and use that expression to substitute into the other equation. It's completely your choice, but I want you to make wise choices and save yourself a little bit of work. Okay, third system of equations. Both x and y have both been solved or isolated. So you could go either way here. I would just go with the easiest or the expression that's going to eliminate the fraction as quickly as possible. So I would choose 4x minus 5 to substitute into the second equation wherever I see y, because I can tell that's going to eliminate that fraction very quickly. Okay, let's put this all together and let's solve some systems algebraically. So it's time to get out your notes, Solving Systems of Equation by Substitution, and open up to the first page, and let's take a look at the steps involved and solve this system. Following the steps that we have listed over here to the right, step number 1 says to solve one of the equations for one of the variables. Your answer will be an expression. Well, guess what? It's already been solved for us, so that step has been accomplished. X has been solved, and it is equal to 2y minus 13. Step 2 says to go ahead and substitute that expression you found in step 1 into the other equation and solve for the second variable. All right, so this one is solved for x, sort of. X is equal to an expression. So we're going to take that expression, 2y minus 13, and substitute it into the first equation wherever we see x. So here's what that'll look like. 2 times x, or our substituted expression, 2y minus 13, plus y equals negative 1. Okay, so let's do our distribution here. That'll give us 4y minus 26 plus y equals negative 1. So that's 1y and 4y will give us 5y minus 26 equals negative 1. Let's add 26 to both sides. That's going to give us 5y equals 25. Divide both sides by 5. And that gives us y equals 5. So I'm beginning to develop my solution. So I'm going to make a little ordered pair up here, and I know that my y value is 5. So I'm going to need to clean up a little bit here. And now I'm ready to go to step 3, which says to substitute that value for the solve variable, so that y equals 5, into one of the equations and solve for the other variable, or solve for x. So I can choose either of these equations at this point. It doesn't matter which one. Let's choose the one that's going to be a little bit easier. X equals 2y minus 13. So x equals 2 times the y value that I just found, 5, minus 13. X equals 10 minus 13, or negative 3. Okay, I just found my x value, so let's put it up here into my ordered pair, and that is tentatively the solution to our system. But let's double check. We just found that final value by using the second equation, substituting the y value in here and getting the corresponding x value. So let's just double check that negative 3, 5 is also a solution to the first equation, 2x plus y equals negative 1. So 2 times my x value, negative 3, plus y, 5, equals negative 1. That's negative 6 plus 5 equals negative 1, or negative 1 equals negative 1 equals negative 1. So true statement, which means the point we substituted in, negative 3, 5, is a solution to the first equation. So we've proven that it's a solution to both, therefore it's a solution to the system. So we just completed step number 4. Substitute those values into the other equation and check that the point's a solution to both equations. This is what it looks like when we solve a system of equations that has one solution. These steps all kind of make sense. But let's take a look at a system that has no solution and see what that looks like algebraically. So we'll follow the steps again. Step 1 says to solve one of the equations for one of the variables. Your answer will be an expression. And that's already been done for us. You can see that y has been solved, and it's equal to this expression, 4/3 x minus 7. Step 2 says to go ahead and use that expression and substitute it into the other equation. So we'll substitute this expression into the first equation wherever we see y. So that will look like this, 4x minus 3 times y from the second equation, y from the second equation is 4/3 x minus 7, and that's all equal to 15. We have some distribution to do, so we've got plus negative 3 and plus negative 7. I'll be distributing that negative 3 to both of these terms. And that'll look like this, 4x minus 4x plus 21 equals 15. So the 4x minus 4x is just going to give us 0. And we're left with this puzzling equation, 21 equals 15. So step 3 is telling us to substitute the value from the solved variable in step 2. But I don't have a value for a variable. I have this untrue statement, 21 equals 15. What this is telling me is that in my second equation, when I substituted this rule for y, I got this nonsense 21 equals 15. What that says is that there's no time when this first equation will have a y value that follows this rule, 4/3 x minus 7. Y will not be equal to 4/3 x minus 7. Both of these rules will never be true at the same time. So this system will not have any solutions. They don't share any points. And remember when we were graphing, that was a system of 2 parallel lines. So how can we double check that in fact we have no solution? Let's see if these lines are actually parallel. This one, the second one, is already in slope-intercept form. So I can see it has a slope of 4/3. Let's take the second one and put it in slope-intercept form and see if these are parallel lines. So 4x minus 3y equals 15. I'm going to solve for y. So I have to subtract 4x from both sides of this equation. That'll give me negative 3y equals negative 4x plus 15. And now I'll divide by negative 3. And that will give me y equals 4/3 x minus 5. So you can see that this first equation, this is just an equivalent version of the first equation. I have a slope of 4/3. Slope is equal to 4/3. And in my second equation, slope is also equal to 4/3. So these are parallel lines, which means they will never meet and they will never share a point. So when we came up with this untrue statement and determined that we have no solution, we were absolutely correct. Let's go back to our steps. Step 3 said to substitute the value for the solved variable into one of the equations and solve for the other variable. Well, we didn't get a value for a variable. We just got this untrue statement. So we're unable to perform step 3 and therefore unable to perform step 4. But what we are able to do when we come up with an untrue statement, let's write a new step 3. Step 3, if we get an untrue statement that doesn't include any variables, then we can check that the lines are parallel. And we do that by putting both lines into slope-intercept form and seeing if they have the same slope. If they do, we know they're parallel lines, and we know that our system will have no solution. And remember, we can also represent that by the empty set. All right, let's take a look at one more final example. In this example, we're looking at a system of equations that is going to give us infinitely many solutions. Let's start off with step 1. It's the same as always. We're going to isolate x or y in one equation. And you can see that y has already been isolated for us, so that step is done. Step 2 says to use that expression and substitute it into the second equation. So if y equals this, we are going to substitute that in wherever we see y in the second equation. That'll give us x plus 2 times y. Y from that first equation is negative 1/2 x plus 4. Right? All that's equal to 8. So we have some distribution to do. We're going to multiply 2 times negative 1/2 x. So first we have x out here, plus 2 times negative 1/2 x. That's just negative x. And 2 times 4 is 8. And that's all equal to 8. X plus negative x is just equal to 0. So we're left with 8 equals 8. Step 3 is telling us to substitute the value for the solved variable into one of the equations and solve for the other variable. But we didn't get a value for a solved variable. We got this true statement, 8 equals 8. So we're not going to be able to perform step 3, and we're not going to be able to perform the following steps. What this means, when we substituted this expression from the first equation into the second equation for y, is it means this rule is not only true for one point, but it's true for every single point. So we have a case where we have infinitely many solutions. And remember what that looks like when we have a graph. That means we basically have the same line and they share every single point. So since we can't double check like we typically do in step 4, the way to double check when you get a true statement like this, and your initial response is that you have infinitely many solutions, is to check and see if you have the same copy, if you have a copy of the same line. Equation number 1 is already in slope-intercept form. So let's put equation number 2 in slope-intercept form and see if we have the same slope and the same y-intercept. We have x plus 2y equals 8. Let's solve for y. So subtract x from both sides. That gives us 2y equals negative x plus 8, and divide both sides by 2. And that gives us, y equals negative 1/2 plus 4. Oops, that's negative 1/2 x. So y equals negative 1/2 x plus 4 is exactly the same as the first equation. So we're now quite certain that we have the same line, right? So the lines might look something like this, lying right on top of each other, and therefore sharing every single point. So the solution to this system, the number of points that these lines share, are infinitely many. They have infinitely many solutions. Okay, so your step 3 should be to check for the same line. And we'll do that by putting both lines in slope-intercept form. Right? So if they have the same slope and the same intercept, they are in fact the same line. And that's our way of double checking instead of the step 3 that we have listed here. Okay, one more thing. Let's sum this all up. This is a chart that shows the types of systems that we've talked about so far. The first type is the type that has one solution. And when we graphed that, these were intersecting lines that shared exactly one point. So they had one solution. When we solve these algebraically, we're going to get x equals some number and y equals some number. And the equations will look like this. They will not have the same slope. They might have the same y-intercept, but as long as they have different slopes, they will eventually intersect at one point. The second type are parallel lines that never ever meet by definition. Therefore, how many shared points can they possibly have? None. So these systems have no solution. What does that look like when we have the equations of the two lines? Well, parallel lines will have exactly the same slope, but they must have different y-intercepts. And what does that look like algebraically? When we try to solve it algebraically before we've graphed and realized that we have parallel lines, we come up with some crazy statement that is completely untrue, like 0 equals 8 or 3 equals negative 2. All right, and finally we have the same or coinciding lines. Those are one or two lines that lie right on top of each other. Therefore, they share every point, and therefore the system has an infinite number of solutions or infinitely many solutions. And in the equations, we're looking for the same slope and the same y-intercepts. Algebraically, we're looking for true statements like 4x equals 4x or 0 equals 0. When we get that true statement, that's an indicator that we have infinitely many solutions, and then we want to look at the equations of the lines to see if we in fact have the same line. So that's it. That sums up types of systems, and we'll be doing a lot more practicing in class, and we'll see you next time.